and welcome back to day number 2 of the intense Java EE workshop for this weekend. And today's topics are going to be UDP, TCP, IP, which is going to be in the next lecture, an orientation or introduction to RMI in terms of how it relates to UDP and TCP, which is the reason why I'm mentioning UDP and TCP and networking concepts, and a little bit on middleware today. Ending with, probably internetworking concepts. And then I will go over as well today UDP and TCP examples. I believe I'm going to maybe just save the RMI for next session because I have a lot of RMI stuff that I want to show you and I don't want to rush through it. But this would make a great topic for the next interactive weekend session. And so our topics for today in terms of this particular lecture, which is lecture number 4, and it also has some source code that goes with it on the bhacker.web website. So what I'll do in this first section here is spend about an hour or so, go over some networking topics, go until I get tired, take a short break, and then we'll hit some source code, and then we'll start looking at some source code stuff. And so you definitely don't need actually the EE version installed for the UDP and the TCP to work. You can actually have just the regular old SDK. And the examples I'll probably show you on a MacBook actually. I don't even have to go to my Windows side for it because it'll work either way. Sockets are sockets. Sockets work on every platform, which is the interesting thing and the reason why I'm mentioning sockets. It's the underlying architecture. In fact, RMI uses the socket concept. It's just a higher level abstraction, an API built on sockets to facilitate the middleware. So I'll be talking about that, and that's really in terms of the topic of interprocess communication, processes that are bound, or threads that are bound to sockets, and they're exchanging messages back and forth. And it does kind of lead into the concept of multi-threaded applications and threaded communication in terms of classical IPC. Very old topic, comes from the Unix days. It has been around since the beginning of networking, beginning of computers in Unix actually. So nothing new. And then we will also kind of take this part here and compare it with more current distributed objects and remote invocation. So today's lecture, this particular one, is going to be very concept-based, but it's going to give you the foundational information. So networking issues of distributed systems. So we had to meet simple application requirements in the old days. In fact, we had a lot of different applications, and we still do. We still have file transfer, remote logins, email, news groups, and they're all separated. And what it was the kind of interesting thing is a lot of people, one group of open source developers were working on, file transfer stuff. Another one was working on something else. And there's not very much unification in terms of the toolkits, but they're all multi-purpose, and that's still pretty good. I mean, that's still definitely the current as well line of growth. But with the growth of the internet, more stringent requirements are necessary in terms of new modes of the use of those particular tools, as well as additional and more stringent requirements for those tools. In fact, a lot of the protocols differ significantly between a lot of the file transfer or telnet, as to say, or SSH logins and shells and things. They vary. Actually, some of them are secure, some of them aren't secure. Some of them run faster, have different types of interfaces to them. In terms of the current network requirements, what we're looking at, the main focus is on performance, obviously. Speed, we'll never get away from that one. Speed in which the individual messages can be transferred back and forth between computers themselves. And when we talk about speed and we measure it and we try to benchmark different types of protocols and different types of tools and utilities, the two kind of, the latency and data transfer rate is basically the only way we're going to be able to measure in terms of the performance. It's not really, how beautiful the GUI looks or something like that. So in terms of latency, and this is your definitional stuff for today, it is a delay that occurs after a send operation is executed before the data starts to arrive at the destination computer. It's called a network latency. How long does it take to get there? And how long is the delay, essentially? And then the data transfer rate is the speed at which the data is actually transferred between the two computers in the network once the transmission has actually begun. So we have the delays that occur through network latency, and then we have also the transfer rate that is usually done in bits per second. If you take a telecommunications course, you'll hear and be able to calculate all of the different, or you probably have taken it already, all of the different ways of measuring bandwidth and capacity, and all sorts of fun little measurements that we can make in terms of bits per seconds and stuff like that. So the message transmission time is the latency plus this length and data transfer rate. So it's really a combination of both. Another issue, I shouldn't say issue, another requirement is that scalability, as I talked about yesterday, the potential for future size of the internet to compensate for population of the planet. I don't know, maybe we'll get to a certain point when the internet will stop growing, but actually not. I mean, right now it's still growing at the same pace, and you get Moore's law, and you get all these other kind of laws that come. All the brilliant people of the world have speculated over the past years how to exponentially measure the exponential growth of the internet and everything that's been going on in terms of increased processor power and hard disk space, and the sheer number of users who are connecting each year. It still seems to be growing at a pretty good rate, which is great. So networks must scale, actually, must be scalable. Another thing we're looking at is reliability and security. And reliability, we don't really hear that much about until you take a quality assurance course, where you start looking at software engineering course, where you start looking at, well, what happens if the thing goes down, or do we need to recover it? What happens when we have communication failures, which is just a reality of life. Security, I think there's an overwhelming number of security issues and security courses these days as well. Making sure we have firewalls, distributed systems encryption, secure lines, SSL, stuff like that, certificates, third-party authentication. Those are all kind of subtopics that end up in the security category, and there's a ton of classes in terms of, I should say school classes, not like object classes, but school classes in terms of security these days. It seems to be a hip concept. One of them, though, that I don't really see as much of is the mobility concept, actually. The internet is mobile, as we've seen with mobile phones and applications and things. So being able to provide devices that have that transparency in terms of the connection to the internet and the connection with the application. So you're running essentially the same utility application or tool on whatever you happen to be connecting to. And then addressing the routing and schemes of the internet in terms of wireless devices, so that they will adapt well, and basically intermittent connections between different subnets and different components on the internet. Wireless is actually still slower than wired, obviously. We haven't gotten to compatible speeds yet, although we keep going 3G, 4G, 5G, 6G, I don't know. I think we're only up to 4G right now. 4G Lite, I guess, is the Verizon one. And actually, you know what? A lot of the 4G stuff is kind of misleading from what I've been reading. It's using fiber optics on the land between the towers and between the infrastructure that's supporting the network, but it's really 3G with fiber on the land. So it's a combination. It's giving you faster than 3G, obviously, but it's not. I don't think it's really 4G. I mean, I think it's 3G plus, or how they market it for 4G Lite. Yeah, and the Lite is actually spelled like light, like LIT, whatever sort. Indicating that it's fiber optic light. So it's a little misleading to the consumer who doesn't understand the differences between wired and non-wired and all the different things. But to transmit a signal off of a satellite, we do have some limitations that have not yet been addressed in terms of making that as fast as it could possibly be. So plus you have weather, you have sheer location, geographic location that affects wireless as well. So long story short, we are making improvements. However, when we take mobile devices, those are all wireless. Nobody walks around tethered to a wall with their mobile device. When we add them into the internet, we put that into a distributed system, it brings down the quality of everything. And so that's kind of a negative, I think, but it's because we're only as fast as our weakest link. And we can't run a server off of a mobile device, but we have to consider that not every device that's connected is going to be of the same speed. And we might actually be going through cellular lines on the network before it even gets to our mobile device. So it kind of really does depend upon the structure and infrastructure, but as a whole, as things start developing, it does get faster and faster as a whole, because everything is getting faster and improved upon the years. So quality of service is another one, and that's a QA course as well. So applications transmitted, multimedia data requiring guaranteed bandwidth and latency. In fact, a lot of the cloud computing stuff is really a factor of getting everybody online and making sure we have consistent speeds. You can't run, and this is one of the bottlenecks that's going to happen in terms of the quality of service. It's sketchy. It's not as bad as it used to be. But right now you can't really rely upon a cloud infrastructure to be actually part of the distributed environment like significantly. I mean, you can definitely put cloud support in there, but until you get constant 24-hour day, 7-day a week, high-speed access everywhere in the world, you can't build as a framework the application that relies on the cloud reliably. I mean, you can build it and it works, but at this point, I think it's beyond experimental at this point. In fact, it's being employed. Comcast, our local provider here in California, uses a cloud for their DVRs. So when you record something, it actually gets recorded on the cloud. But I've experimented with it myself, and I've noticed that download speed kind of varies. It varies with how fast my DSL connection works. And when my connection kind of goes a little buggy, my TV quality is just crap. I'd rather just watch it live at that point. But again, if I upgraded to their Comcast digital network, I might actually have better success with that, but I just don't want to pay their price. So it's expensive, actually, and that's what we're seeing right now. So as as the future grows, everything is cheaper and everything gets faster and better. So long story short, multicasting is another concept that's been around for a while, but it is also still part of the distributed environment. The one-to-many communications need for distributed systems to be able to broadcast mass quantities of messages from one point to many different points. So you guys are all graduate students, and you already have taken a networking course, so you all know about these acronyms. So I'm going to spend 2 seconds on this slide. LANs, WANs, PANs, and MANs. It depends on the size of the network. If you're not familiar with networking and never took a networking course before, it's slide number 9. Read this slide. It'll give you the definition of all these different types of networks that you may have listed. More currently, however, what we're looking at is WLANs, which you may not have gotten in your previous course, or WMANs. So we don't have it yet. Actually, we do have it. I think the city of Cupertino, don't quote me on this, maybe it's Sunnyvale or Cupertino, there is a wide area wireless network in the metropolitan city, and would be considered a WMan. We don't have very many of them yet. In fact, this is just a skeptical rumor, and I heard it was actually shut down. But the local governments, local cities, and especially in the state of California, have recently decided that they should be providing utilities, like internet access. Because actually, believe it or not, if you think about the concept, the government is generally in regulation or regulates, and it has been regulating the telecommunications industry until 1996, until they deregulated it. But they still have a lot of regulation on power, electricity, gas, water, all of the basic utilities of life. And the current modern view is that wireless access, or that internet access, is sort of becoming a utility. I mean, if it's something everybody's having. There's a lot of controversy over that concept and the government control over it. And in fact, if you have been watching the news lately, they also want to regulate the internet. They want to step in, and they're trying to step in terms of this is all the companies I think it was like last week or the week before, censoring the internet. Well, it's government control. They want to step in where they don't believe they should. I personally don't believe they should step in on that. Yeah, sure, they can give us wireless access in our metropolitan area, but don't regulate our internet. So what they want to do is start, charging taxes for people who buy and sell stuff. They want, actually just buying, I guess, selling. When you buy something, actually when you buy something, you're supposed to pay sales tax to as well. So commerce, illegal substances. There's companies on the internet that are selling alcohol and cigarettes to minors, and not to mention drugs, not to mention prescription stuff. There's a lot of laws being broken on the internet, and the government sees that. The government wants to censor everything, copyright protection, music rights, you name it. It's going to ruin the concept, in my opinion. And long story short, going back to the networking component, they also want to build wireless WMANs in metropolitan areas. It has been unsuccessful so far. We don't see it. I know some of you guys aren't really from California, or not really, some of you aren't even from the United States, but We have, I can tell you honestly myself, in the last year we've seen a lot of coming and going of different ideas and plans, and nothing has really stuck yet, and it hasn't really hit the media yet. But there has been a couple of things, and I want to say it was Cupertino or Sunnyvale, and it might actually still be up, don't quote me on that. You can do some Google research later and find out. But I believe the problem was with the expense of the towers and with the broadcasting the signal, and the technology infrastructure was too expensive. And, you know, everybody knows that California is a budget crisis right now, huh? Sunnyvale, you think? Yeah. I don't live in Sunnyvale, so I don't live in the town that it was in. So, is it still going on? You did hear about it, yeah. I believe it might still be going on. I don't know how you get access to it. It's supposed to be free, actually. So, most people around here get free internet from their neighbors. We don't lock it down. But anyway, that's my spiel on that. That's kind of the future, bringing this back into the future, present, future. So these topics are definitely relevant to today's commerce and today's environment. So different types of networks in the distributed system. I'm going to talk a little bit about the concepts of intranetworking and intranetworking and the concepts of the distributed environment in terms of the infrastructure. And this is really an infrastructure kind of lecture. The next one is going to be on IP and the internet protocols. But to give you the big picture, what we're looking at are the subsystems of the various different networks that are linked together. We're calling this the internet. Is it really the internet? Well, we got different labels for it now. We have the World Wide Web 2.0, we got the 3.0, we got the, actually we're on 2.0 now. There's so many different labels on this because people don't like to, you know, internet sounds old, I guess, right now. So you got to call it 2.0, I believe, is the seamless integration of widgets and things where they're connected to the internet with their applications, and it also entails a bunch of other things. And 3.0, I believe, is the virtual reality component of it, the gaming and the realism. So you don't know if you're on the internet or off the internet. And I guess 4.0 is you're on the internet 24 hours a day, 7 days a week, and you're not off of it. So I mean, it'd be nice if the internet followed me around. Unfortunately, I think the internet is probably growing faster than the applications that are on it. So it'll take some growth before we can actually see the invention or the use of it. Now everybody knows we have the WW2. Well, actually, we have the second. So the internet itself, the World Wide Web, has become so populated with commercial and I shouldn't say dishonest, but hackers and all sorts of things that need to be regulated by the government. Now we have this separate university going back to the grassroots. There's a separate internet that's actually out where universities and researchers and professors, non-commercial people, get on that, and it's like a separate second internet, but it's not for commercial use. There's no eBay on it, kind of thing. But I think the Wave is actually too separated out. Actually, I have multiple versions, and well, the Wave, the current picture right now is like that. So in terms of network performance, this is again, I'll spend 2 seconds on this because you've already had this hopefully in a networking class before. But looking at the various different concepts in terms of how the range, the bandwidth, and the latency play an effect. And part of the skill in developing applications for the distributed environment is keeping all of this information in line and being able to actually build applications that work correctly or work successfully. One of the side notes here, because I kind of put my mouse on Bluetooth and I went, oh, Bluetooth. Good, huge area of growth right now. In fact, especially with the mobile market, Bluetooth to Bluetooth communication between consumers, and then also Bluetooth tracking. You may not realize it, but most 99.9% of all phones have Bluetooth on them, you know, because everyone's using a hands-free Bluetooth headphone on it. So I recently came across, personally, a company that's selling sensor equipment. So as an example, you're in your car and you're driving down the freeway. You can actually see how many people are around you. You can see how populated the area is. If you are in a retail mall, you can actually track how many, let's say you own a store in a mall, you get one of these sensor devices, and right now there's no applications on the market for it, but you can easily, you know, with a Linux background or whatever, put one together. Works right on it's a hardware device. Counts how many people have walked into your store, because everyone's carrying a phone, and because with that assumption, You can't count kids. Well, actually, kids have phones too. You know, babies you're not really interested in. You want customers. You want to track customers. You can check traffic. It's people watching, essentially. It's better than a surveillance camera because you can tell, did anyone go into this room? Was there a phone? And it just basically takes and captures and keeps track of the Bluetooth connectivity, and you can actually set IDs associated with, because the devices actually pick up, sense the Bluetooth codes and things. So you can pretty much not only people watch, but do statistics on people, traffic zones, buses, cars, freeways, anything you wanted to essentially, and track people with it. So there's actually a couple of different applications in the makings right now with that technology. And the interesting thing is one of the holdbacks of Bluetooth in general was the limited range. And the pros to Bluetooth, just to give you not to repeat your networking course, but it doesn't eat up that much battery. So you can have run a year on an itsy-bitsy little battery. So you can make small devices with it, like headphones and stuff. Although those headphones don't last too long. Or the earpieces don't last that long. Long story short, it's supposed to get better battery life. The problem with it is it's got limited range. Also limited security right now. And the limited security is kind of you pick that up, put a high antenna on it, get a receiver. So you have one antenna, one of the devices got a strong receiver. You have increased the range, and now you can go spy on everybody who's got Bluetooth in the next mile from here or something, or the next half a mile or something, which are the devices that are coming out, which makes it a wide area instead of a local in terms of the connectivity. So what's going to end up happening in the future is perhaps maybe we'll take that Bluetooth concept and we'll have devices that have their own high-powered antennas on them. So if we can increase the range of Bluetooth in general, we've got a better than infrared, better than a lot of the different other types of devices, and it lends itself out. As long as people are carrying Bluetooth with them, lends themselves open to some interesting applications. And what I've been talking about are actually protocols. And we've all had this in networking as well. It refers to the well-known set of rules and formats to communicate between processors. Two parts of it is the specification, the sequence of messages that must be exchanged, and also the format of the data. And I'm going to kind of go fly through this stuff because you guys have had it before, hopefully. But protocols are the rules in here, and everyone has seen this maybe before, I don't know, the layering approach, the concept of layering protocol software. And people look at this and then they start running out of the room because this is the, kind of the basis of the OSI model. And people go, oh no, not OSI. So if we want to be able to interconnect components and software and hardware and things along the network, we have to have some sort of networking interface, and we have to regulate it. Going back to those rules. Not really a regulation, not by the government. Actually, the government has no say in this at all. It's mostly driven by developers, IEEE, ISO, people out there in the industry that are setting standards, and the standard essentially ensures interconnectivity. So if you don't understand, if you've never understood the OSI model, which a lot of students just run away from, just think of it sort of like a layering approach in which you have a message sent from point A to point B, sender and receiver in the communication channel. The layering is defining the protocols that are going to be used at each one of the different layers. And the layers themselves are divided out by their task or their function. And at the lower level, we generally have the hardware, and at the top level, we generally have the application. So you can call it hardware physical layer, application layer on the top. Most people memorize the OSI model. It's like, what is it? All people seem to need data processing. So the A for all stands for application, P for presentation, all the way through the line. So protocol layers. But you know what, though, it actually makes absolutely no sense. In fact, when I was taking Novell courses years ago, back when Novell started becoming popular, and they made us memorize the OSI model. This is like, I don't know, 20 years ago, 15 years ago or so. And yeah, sure, I memorized it. But for the scope of the certification for that program, it didn't have any relevance. It didn't have any meaning to it because it was all application level stuff. A little bit of networking in there, a little bit of data in there, but it was all in the presentation application layer in terms of, well, I shouldn't say. The transport layer was also used a lot, but it didn't take too much to pass the test. All you had to do was memorize the OSI model. So nowadays I'm pretty sure it's much different, perhaps. In fact, I don't even know what, this was like version 3 or 2 or 3. I don't know what version they're up. Do you know? Is Novell still out? No, I don't. Novell doesn't even exist anymore. Yeah. Do they? They're probably Linux now, or I don't know. SUSE or whatever, Linux, Sushi Linux bought them, or they bought them or something, and now they're still doing some Linux support stuff. I don't know, don't quote me on that, totally wrong. Protocol layers. Anyway, so just to describe this in terms of the networking software, it's arranged in a hierarchy of layers, and so the hierarchy of layers in the previous slide showing that the above, what presents an interface to it, so what basically that text is trying to tell you is that this layer deals with this layer, this deals with this layer. We not only have the interfaces that's going back and forth between the sender and the receiver, which is defined by the protocol, we also have the information that's going up this way, that's defined by how the layers themselves are communicating with each other. And so the layers present the interface to the layers as well. And the sending side, each layer, except the top, accepts an item and from a specific format from the layer above it and below it, and applies it to the transformation or encapsulation of the data of the packet or the information that's thrown back and forth. The receiving side does the opposite. It takes the information that's received, converts it, transforms it back into the data, and uses it, and then it passes information to the layer below it. The reason why we don't have anything up here is because this is the all people. This is the application, and then we have the presentation underneath it. Then the session data, and then transport. Usually when we talk about networking, and today UDP and TCP is working with the transport layer. The transport layer is nothing more than connecting the sockets, taking the sockets and then bringing it back up to the presentation of that abstraction and then to the application that's being used. What are the applications? Well, you can actually build a nice chat program using TCP and UDP. Actually, it's more of a UDP. Actually, well, no, you gotta have a constant connection. I'll go through that in a few minutes. But it's still being used actually. Ports as an abstraction and sockets that are bound to ports still being used, not outdated. Every one of your chat programs out there is bound to a port. Actually, your HTTP server, your Apache server is using a port and a socket abstraction. And that's what you're going to be using, or your Glassfish is also doing that too. And that's where you lead to security issues when you start opening up ports and allowing traffic to come into them. Okay, so encapsulation as it is applied to the layers themselves as an example. Here's our all people seem to need, going down this way, data processing, the data and the physical layer. There's not very much abstraction on the data and the physical. The physical layer is going to be the protocols for the MAC address and the information that's on the hardware itself, the internet card, or the device that's enabling the connectivity via the physical, either wire or wireless kind of connection. And the data is going to be nothing more than the format of the sending and receiving of those packets / datagram or whatever happens to be associated with that communication protocol. So the tags and the headers are the protocol types for the layers above. These are the tags needed for receiving a protocol stack to correctly unpack the packets. So TCP is actually kind of an interesting protocol. Believe it or not, it's been around since the beginning, and every single computer, Windows computer actually, that connects to the internet is using TCP. So in the old days, actually in Windows, we actually had to install a TCP IP driver, and we had to actually, bind the driver to the internet card, and it was actually a little bit more manual. Now you just turn your computer on and it automatically connects. But the wired connections in the earlier days had special drivers and stuff for it. Now we don't think about that. In terms of the protocol suite, as I mentioned before, this is kind of a summary of what I've just talked about. The complete set of protocols is referred to as the protocol suite or protocol stack for your terminology. And this is the OSI model, the model for open systems interconnection. Nobody owns the model. It's not. This is actually standardized, believe it or not. We also have another model called the Department of Defense, the DoD model, as a side note. And that model is standardized by the government, actually. And it's very similar to the top layers of the OSI model. And someone came around real recently, and this is the most pathetic thing I've ever seen. In the old days, we had 7 layers of the OSI model. I grew up with 7 layers of it. Now we have 5. They're mixing the layers together, and I can tell you why, actually. Because somewhere around here, all of a sudden the abstraction got bigger. And now we can say that actually it was right around the session, the transport, and the network. It's the session and the transport sort of came into one with middleware. And so now, some textbooks are still teaching it with 7 layers. A lot of them have switched to 5 layers because students can't. And then if you learn it with 5 layers, you're missing out on the details of what is the transport and what is the session and what is the network, actually, because the distinction and the layer cut ended up right into this kind of area. And only because a lot of it did start to merge, and a lot of the newer protocols, oops, I didn't go back too far. A lot of the newer protocol suites, especially the DoD model, puts them together. And so, the modern day model is stripped down. I don't think it's any easier to learn 5 versus 7. And I think that, the original intent was to separate it out, but now we have so much blur in between the different layers, a couple of different areas. So, long story short, students today aren't learning the whole OSI model. They're only learning part of it because, they go, oh, we don't need it anymore. Okay. It's kind of like learning, actually, on a different kind of parallel example. It's kind of like how modern day high schoolers are learning computers. They're not learning anything about computers. They're learning how to press the on and off button and how to check email. They have no idea how the computer actually works. And we're getting dumber and dumber as the technology gets better and better. So, which is, means that we're not going to have as many computer science students. Actually, we don't have as many computer science students today as we had, 10 years ago, when people actually had an interest in it. Now they just take it for granted and just turn it on. So why study it? It's good. So anyway, it means more jobs for those people who do have a background in it. So protocol layers begins substantial benefit for simplifying and generalizing the software interfaces. Also carries significant performance cost. Why do you think this is so? Performance cost. If you think about the concept, and I'll answer the question for you. If you think about the concept of communication, the more people you have to communicate with, the more you got to talk, or the more you got to communicate and send and receive. The more you layer it out in terms of the abstraction, the more communication you have to do between the layers. That passing and sending and that communication takes up bandwidth. Not to say that it's bad bandwidth, but it does hit. The more you go, the more layers. And here's actually the 7 layers. I refuse to transform to the 5 layers. So we have 7 layers, and here's all people seem to need data processing. Is my mnemonic for that. And this actually comes into play, and I'm going to compare the TCP and the UDP to this model, and you're going to go, why are we looking at every student goes, why are we even going to bother with this? It's the underlying concept of RMI. It's how RMI was built. In fact, this is the underlying implementation of RMI. RMI is nothing more than a higher level abstraction on top of this. Instead of making the programmer manually open a socket and bind it, instead they click on a button and they say, establish a connection. It's just a higher level interface to this. But this has some relevance in terms of your overall understanding of it. This is slide number 19. If you've never seen this, I am not going to spend time in this lecture going over this model because every undergraduate student who's ever taken a networking course, and if you haven't taken it, take it. Or, even if you're transferring from a different major, you're a business student studying computer science now. Slide number 19, you can read all about all the different things, and basically each layer has a different responsibility associated with it. So now let's look at, well, actually this lecture jumps right into internet protocols without even talking about this IP. If you're brand new, well, if you have taken your networking course, you know that IP is a separate protocol than UDP and TCP, and that's why this line is here. Although, you're not going to believe this in a million years, but now they're starting to write this without the dash. I see it all over the internet. TCP IP with no dash in it. It's like one protocol. Oh wow, that's like totally misleading. Because, it works together. Why I put the dash in there, right? It's all one word. Or they just say TCP, and they assume that IP is underneath. Well, what is IP? Well, that's the addressing scheme. It's the internet protocol. It's the addressing scheme. it's right here. It's on the network layer. TCP is on the transport layer. They're two separate layers. UDP is on the transport layer. IP is the network layer. IP is what holds the string, the glue together on the internet. It's the common language of the addressing scheme. It's how we find computers and things. And we will always have IP, so you can't take IP out of the picture. So it's grown to over 60 million hosts, and I have the next lecture actually is going to go through IP, IP4 versus IP6. This is again not a networking course of basic fundamentals, so but I will point out some of the things that have been changing and expanding just to review the concept, but not in this lecture. Example application services protocols that are based on TCP IP. Well, the HTTP is. And this is where we're getting our hypertext transport protocol, and our POP, and our SMTP, and our NNTP, our net news groups, file transfers, FTPs, and telnets are all based on TCP. So until these applications go away, we're still on TCP. In fact, we still have TCP. We have TCP with RMI, actually. You can't run RMI without TCP protocols. So here's our network-specific frame in terms of the network interface, the underlying network that's underneath it are IP datagrams. It is datagram. It's not that's the kind of interesting connection. IP is not connection-oriented. It's connectionless. It's datagram. And that's one of the things I'm going to kind of hit today with our example between UDP versus TCP and why we want to use it. It's stateless. Yeah, UDP doesn't have states. TCP has states. IP doesn't have states. So one of the problems in terms of the growth of TCP and the changing of it, the increase in the overhead of the tracking of the messages just to do a connect is like 3 messages that are passing back and forth on a TCP connection, where you don't have anything on a UDP. So there's actually a lot of growth in terms of the UDP component because it's faster and less reliable, however. But we're working on a stateless datagram IP protocol, and the message formats themselves are the streams. This is where we get the stream behavior in RMI on top of the abstraction of the TCP, actually, on top of the IP. So this is all incorporated into the fundamental lower level implementation of the higher level RMI. And you'll see once we start looking at this, that RMI is nothing more than abstraction on top of sockets, essentially. So here we have, and you guys probably know this already, so I'll kind of flip through this here. 2 transport protocols, TCP and UDP. TCP is the reliable connection-oriented. UDP is the datagram protocol that does not guarantee reliable transmission. No guarantee, there's no error checking, there's no packet, there's no messages, status messages, and there's no log either. IP is the underlying network protocol. IP diagrams provide the basic transmission mechanism for the internet over TCP networks. It's UDP/TCP. You never see that going on because UDP is not used for very much, not as well used as TCP. Internet protocols are usually layered over other network technologies as well, such as the Ethernet packet format and the Ethernet protocol. And this is something your average Windows user doesn't really understand either. You have IP, but IP has something underneath it. It has Ethernet underneath, or has another. It doesn't need to be Ethernet. It could be another type of protocol underneath it. It's giving us our frame packet for Ethernet headers, and then we have our TCP IP header packet, and then we have our TCP packet or port that's being used associated with the header of the message themselves. And we're looking at the concept of the format of the Ethernet frame, going back to networking again. So we're still in a frame. This is still relevant. This has been around since the 70s or so. I don't know, maybe the late 60s. I don't know. Don't quote me on that. It's been around forever. Still being used. Still relevant. This is still our foundation, our architecture. So we have IP, then we have the application built on TCP, we have the application built on UDP. So it's a conceptual view. Take a few moments to address the concept of the addressing scheme of IP, chosen for naming the address hosts of the routing IP packets to their destination. And a lot of people say, well, this is one of the reasons why we went from IP4 to IP6, because we need more addresses. Yeah. And also, there's more changes than that, however, too. The packet size changed. So we went to a higher, instead of a 32-bit, we extended it. We extended the header information to store more information, because what ends up happening throughout the years, we have more sophisticated, specificated protocols running on top of IP that need more support in terms of the packet header and the type of information that we're going to store up there. Now we have more flexibility with IP6, but we're still backward compatible to IP4. The entire internet has not switched over to IP6 yet. So that's one of the other issues when you're starting to deal with, if I'm not going to use RMI, I'm going to use something else, and I'm going to make my own application with this. I still got to be backward compatible. Otherwise, my messages are going to fail because they're going to hit an IP4 network subnet, and they're going to get stuck because they're looking for a piece of paper. The router's looking for something that it can't find. So that's going to be tough, getting everybody on this 6, getting rid of it. And then by that happens, we'll have 7, 8, 9, 10. Actually, we'll end up with 8. So let's see, network identifier uniquely identifies one of the subnets in the internet. The host identifier itself identifying at least the host's connection of that internet as well. Here's the lovely slide that we all remember from the networking course, all the different classes of internet addresses in the internet addressing space. I'm not going to go through this because you've already had this hopefully. But we do have, and just pointing out, the host ID, the network ID, and the multicast address. And it's really an addressing scheme in terms of the communication. It's kind of like when you send a letter in the U.S. mail or any mail, you've got to have a return address, and you have to have a to and a from on there, and a stamp. So you don't have to put a stamp. Well, actually, you do put a stamp. The stamp is that frame inside of the packet, but it's an electronic stamp that gets put on this particular IP address that's going. So providing a communication capability for the internet in the form of its useful application and programs, the transport protocols must provide process-to-process communication, which is kind of the reason why I'm mentioning this, accomplished by using ports. So the port numbers are used for addressing messages and processes with particular computers. And for valid computers, once an IP packet has been delivered to its destination host, the TCP or the UDP layer software dispatches its process via the specific port at that host. So it's basically port-driven. We bind the socket to the port. The socket is created of a particular type, depending upon the protocol that we're using. And in terms of the features of UDP, it's encapsulated inside of an IP packet. And so is TCP. It's actually a smaller packet. It's a shorter header. So short header with the source. Actually, I shouldn't say that. It depends on if it's an Ethernet network. They're all the same size. But with a source and a destination port number, length of the field, checksum on the end of it. UDP does not guarantee delivery. Adds no additional reliability mechanism except for the checksum, which is actually optional. You don't have to implement the checksum on that packet. And actually, it's referred to as a datagram versus a packet normally. Uses restricted to applications and services that don't require reliable delivery or single or multiple messages themselves. You could probably think of some applications, protocols that are based on UDP. SMTP. Separate protocol itself, but it uses a datagram unreliable packet. So when we send an email message, it would be nice to have confirmation. In fact, you can do a fake one. Recipient, you press the link and it sends a message back, but you're sending 2 datagrams instead of 1 in that case. And it adds to the traffic. But SMTP is a separate protocol in itself, but it's based on the datagram packet. It's based on unreliable data transport. So it's just an extension, but it's I'm sorry. It's an extension of UDP. Well, and a separate implementation of a similar concept of UDP. So it still has relevance in today's communication. In fact, there are broadcast messages, message broadcasting. You're on a network. Nobody does this anymore. But in the old days, you were on an intranet. Everybody was connected together. You could say, hey, it's lunchtime. And it goes out to 15 million people. Time to go home. It goes out. Broadcast messaging is all UDP. So basically, I describe to my undergraduate students when I go through a full UDP lecture, it's like taking a ball and throwing it across the street. That's UDP. If you take like a basketball and you just throw it, you stay on this side of the street and you just throw it to the guy on the other side of the street. And TCP is you take the ball and you dribble it like a basketball player, and you follow the ball all the way to the other side of the street. That's TCP because it's managed. There's something that's going along with it, and what's going along with it is a message exchange. So tossing a ball is just one packet. TCP, to toss the ball, it's actually 3 packets to actually get it there, and then it's 3 or 4, to close the connection. And then it's a lot more traffic, a lot more dribbling going on with that ball. It's managed. So it provides much more sophisticated transport service, reliable delivery for long sequences of bytes, guarantees the delivery of the receiving process of all of the data represented from the TCP software by sending a process in the same order. The order in which the packets arrive and don't arrive is kind of not really determinable. In fact, nobody has got that down to a science yet. But there's a particular order of the communication of the managed dribbling of that ball. So that's ordered. But how the ball actually makes it over there, the route that's taken is totally and how the pieces end up getting there, totally unordered. Provides transmission, retransmission if necessary. Send it again if it wasn't done correctly. And done when it does not receive an acknowledgement after the receiving process within a specific timeout period of time. It never receives it, so instead it sends a message back and says, hey, I didn't get it. Can you send it again? The ball never arrived. Can you send me another ball? So, and one thing to actually kind of make as a kind of a point here is that the datagram transport over the, let's take a look at the packet for a second actually. The datagram transport is almost, it's similar. Everything is traveling in frames if it's on an Ethernet network. It depends on the IP packet format as to how it's going to fly over IP. But one message is broken out into several different sized data chunks. It's actually the same, whether it's TCP or UDP. The flow of it over the network is all the same. And the way I describe that to my undergraduate students is I say it's like the sushi boats, the sushi boats that go around in the sushi bar. You guys familiar with sushi? You guys eat sushi? Yeah. Fish. Yeah. So each boat only carries like 3 or 4 packets or pieces of fish, and they float around. But exactly what piece of fish you're going to get first is kind of an unknown because it depends on what boat flies. Yeah, it's usually raw fish. And then the person next to you will pick something up right before you get it, or somebody else. That's kind of like datagram packets flowing over an IP network. The IP network are the boats, or the frames. And inside of them you got the pieces of the sushi. The order in which they arrive to you, how I eat my dinner at a sushi bar is going to be different every time I go. Unless I wait. And that's really inefficient. I'll be there for an hour waiting for, if I want to eat a piece of salmon before I eat a piece of tuna, before I eat a piece of I don't know, salad or something like that. I don't know, something else. If I want that exact order, I'm never going to get it. Well, not in an efficient amount of time. Instead, I'm just going to take whatever arrives. So it's actually kind of like how the internet works. In a lot of ways, and those get datagram packets. But there's a lot more to the sushi boat story, but I'll leave that one because this isn't a networking class. Let's talk about middleware because this is where we're talking. This is what we're talking about in this class. So what do we have? This is why we're mentioning UDP and TCP. It is the lower level. It is the abstraction that everything else is actually turning into. And what are we turning into? The middleware layers is why they call it middleware. It rides in the middle. So yesterday I gave you a description of middleware, and I said, what's the thing that holds the glue that holds the network together? It is. What's the glue? What are the pieces it's holding together? It's holding together UDP and TCP and socket abstractions. And it's also holding together everything on top of it in terms of the services from the network layer. So down at the transport, what we're looking at is request rely protocols. We're looking at marshalling, and I'll talk about that in a few minutes. External data representation. We're also looking at this higher level utility. So RMI is built on top of the infrastructure in terms of the middle layers for the underlying implementation of UDP and TCP, bottom line. And then UDP and UCP, if I were to draw something underneath this, would be IP, if I were to finish the chart out. So looking at the IPC, Interprocess Communication, from the programmer's point of view perspective, we have remote method invocation from our Java EE. And we have a remote procedure call. Both of them are supported in Java, actually. 2 separate two separate protocol, two separate application techniques, and then we write the applications and the services on top of that. So this is the kind of the big picture where everything is going to sort of fit in to our RMI. So let's take a look at the interprocess communication component of it from the distributed systems perspective, relying upon the data exchange, the archiving of synchronization, exchanging data among different types of systems. What we're looking at, and this goes back to classic Unix, we have two forms of IPC. It's either shared message or shared variables or message passing. So we either have direct or we have indirect, if you want to think of it that way, communication channels in terms of the passing of the messages. And so the message passing in the concurrent programming languages, we're looking at language extension and API calls. So the API call would be through the RMI, which would be handling the message exchange for us in terms of how that protocol fits in. The principles of IPC are going to give us the concurrent programs. It's going to give us the concurrently running processes. So I wouldn't call RMI a virtual machine, and I'd call it middleware, but I would actually mostly call it an information broker. It's taking information from different sources and it's brokering it. It's like insurance brokers. You go to the insurance broker and you say, this is how much I want to pay, and he goes out to 25 million different companies and gives you a couple quotes back, and you pick one you like. And he facilitates the communication for you. You don't actually buy insurance from this broker. You buy it from whatever company he comes back with. That's what RMI is doing. So it's establishing the connection between the ports, it's establishing the communication, the message passing, the exchange, the protocols that are implemented underneath the hood. The stuff, sending the messages underneath the hood to the UDP or the TCP or the IP to essentially facilitate the communication. So in terms of the concurrent programs, it's collecting two or more sequential programs executing concurrently, client servers, multiple applications on one server, collecting two or more sequential programs in operation, executing concurrently. Some characteristics of the IPC environment is the message passing between the pairs of the processes that can be supported by two message communication protocols, the send and the receive. And this gets, this reminds me of Unix actually, the sending and the receiving IPC, which is the basis actually, if you think about it. In terms of the concept, Unix, the entire internet is Unix, so it's all IPC. So in order for one process to communicate with another, one process sends a message of sequence of bytes, and then the other process or the destination receives it. We're looking at synchronization. So RMI has a lot of built-in synchronization in terms of the interprocess communication, because what you don't want are, going back to operating systems now, classic synchronization issues, deadlocks, starvation, greedy processes and stuff like that. So what do we have? We're busy waiting. I always like the busy. In fact, you will get some busy waiting with RMI actually, because it uses a block. RMI actually does a block and a send. So it'll block processes until one process is finished. So other processes will be busy waiting for their turn, which is one of the, if you notice it, actually if you compare the speed of an RMI running application with some of the other types of networking middlewares, that's the one thing I've noticed actually. There's a lot of wait. And it's inconsistent. Like sometimes it'll wait a little bit and then it'll flow easily. It's like, because it's either doing deadlock detection or it's doing a busy wait or something. And everybody knows you add deadlock detection to an operating system, you might as well just go get a cup of coffee every time you double click on a program to run it, because it's going to sit there and run slowly. So synchronization, sending and receiving every message, both sending and receiving, are blocking operations, and the blocking operation is true for RMI, as I mentioned. Whenever you send, and that's not a reason not to use it, actually. It's just one of the things you'll notice when you do start using it, or maybe you haven't noticed it. Maybe also depends on the type of application you're building as well, whether or not you're going to end up into blocking situations. So blocking means a send is issued, the sending process or thread is blocked until the corresponding receive is issued. When a receive is issued, the process or the thread blocks until the message actually arrives on receive. In terms of asynchronous, it's non-blocking. This is why people like UDP actually, because UDP is asynchronous. It's not happening in real time. I mean, there's no synchronization between process threads. So send is non-blocking. The send is just throw the ball across the street. I don't have to wait for anyone over there to catch it. Hopefully somebody will catch it. So the sending process is allowed to proceed as soon as the message has been copied to the local buffer. Using a message exchanger buffer is actually good. In fact, this is the nature of an asynchronous, although it is synchronous. If you ever think about the concept of text messaging, if you ever think about the concept of chat, internet chatting, you're sending a message to a server, the server is sending it back. It's non-blocking. You can send as many messages as you want while the other people are sending as many messages as they want. The server is sending the messages out. Whether the messages make it there, what order they make it in, who knows? Nothing's guaranteed. It's a message exchange. It's a middleman sitting between a bunch of clients who are passing messages back and forth to the different clients depending upon who sent what to who. And you have instant messaging, or actually, yeah, instant messaging, chat programs. I shouldn't say text message because that's a slightly different protocol, but it's actually kind of the same concept. Instead of sending it to a server, you're sending it to a cellular provider. Cellular provider is routing it through a network, going to another cellular provider. So really it's kind of the same concept. It's non-blocking asynchronous communication. The receive operation can have blocking and non-blocking variants to it, depending upon what the application is doing. Non-blocking receiving process proceeds with its program after issuing a receive operation, which provides a buffer to be filled into the background. Most separately, receiving notification, that is a buffer that has been filled, or a pooling or an interrupt or something that triggers. You have buffered I/O when, for example, actually you can do this with copying a file. You can implement a CP copy command in a Unix environment that uses a shared buffer with two processes that are working in a non-blocking asynchronous fashion, where one of them is reading from a file and writing it to the buffer, and then the other one waits for the buffer to fill. Because why pull out every single byte that happens? Unless it's going to do that, it's working on its own island of its own, going to the buffer, reading asynchronously as many files as many bytes as it wants, and it's writing it out to a file. So you've got two processes that are sharing a buffer, reading and writing for different purposes. So depending upon what the second guy is doing, it might wait. In fact, it'd be nice to wait, save it up a little bit. Otherwise, you got a lot of busy work going on. It's kind of like putting out a house fire with a bunch of buckets instead of grabbing a hose, essentially. All right, not to mention, I've never experienced a house fire before, but I would hope that they came with a hose and not a bunch of buckets. That's like the slow way. All right, so today's systems do not generally provide the non-blocking form of receive because it adds complexity to the application. So it does add complexity. Sockets. Both UDP and TCP use socket abstractions. Provides the endpoint for Unix between processes, and yes, this is the original BSD Unix. But in all Unix flavors, and Linux also uses sockets abstraction. In fact, you're going to see on my MacBook, I have sockets, and I also have ports that I'm going to use in these applications I'm going to show you. So IPC also consists of transmitting a message between the sockets, between a socket in one process and a socket in another process. The interesting thing, and the reason why we can kind of do this all on one computer, is because if I open two terminal prompts and I run two programs, I have two different processes. They're in terminal shells, and they're running on the same computer. And they're on two separate, that can actually bind the process to a port and actually send it out to the same port between the two different shells because it's all on the same computer. Or I can use two different ports if I wanted to. If I were using IP, I'd bind the address to the port and then I could send it over the network. Or I could bind the MAC address to the port and send it on an Ethernet frame or something over the network. So here we have the form of communication, and believe it or not, this is the underlying RMI, actually. I'm going to see it compared to RMI soon. But the socket here on the client, we have a socket here on the server, and the socket any port. In fact, that's an interesting thing about ports is we got 1,000, we got tons of ports on a computer. You just pick one at random. And if you're on the computer communicating to the computer itself, doesn't matter, there's no security. One thing you will run into, and I will warn you about this ahead of time. I'm going to demonstrate this to you on a MacBook. Actually, I could do it in my Windows as well because I don't have any antivirus software and I don't have any firewall software on this entire computer because it's a MacBook and I don't need it. On your Windows 7 machine or on your, actually especially on Windows 7, and especially on an XP, it might be a little bit easier for you to demonstrate this on for yourself because you'll have to write a program that does this. And when I go through the assignments, you'll see which one that is. But you're going to run into issues where the ports are blocked because your firewall, especially if you're using Norton anything is going to block those ports. So you'll have to disable all of your I would just disconnect from the internet. You don't need an internet connection while testing this. Disable your firewalls, disable your antivirus, disable everything, and it'll work for you. With everything on, you got security. That is what your security software is protecting you. This is what your firewall software is doing for you. It's blocking this stuff. So I don't need to block this stuff because I'm not on a Windows machine essentially. So that's why a lot of people actually like to develop on MacBooks because there's fewer issues anyway in terms of you don't have the same security issues because not everybody is interested in making a virus for a MacBook, but for Mac software. Most people who write viruses are targeting Windows users, so you don't really have to worry about that on a MacBook. So I don't run. In fact, the other thing too is if you run Parallels with my XP and my MacBook, I don't need antivirus software for that either. It gets filtered through the internet, gets filtered through my Mac. Yeah, so even though it's Windows running on a MacBook, it's filtered through the OS X. No, you don't have to load antivirus. You don't have to load anything, firewalls, nothing like that. Through the VM. I haven't tried VMware. I know that Parallels is the one I use. It's just like VMware. It's a virtual machine abstraction. It has a direct connection, and you click an icon, you click on an option that says use the Mac security, use the Mac filter, and it goes through my Mac. It goes through the Mac first, and then it goes to Windows. So it won't make it past the Mac. So it won't make it to the Windows to cause a problem. I'll never get a virus. I'll never get a worm or anything on it through that. I don't know what VMware has. Don't quote me on that. I'm sure they have something similar because it's just as popular. But without all of that stuff, it does run faster in a virtual machine environment. But a virtual machine is always going to run slower anyway than a native machine. So it has its pros and cons, actually. Sockets and ports, let's put it together. So for a process to receive a message, its socket must be bound to a local port and one of the internet addresses of the computer on which it runs. You can also use localhost if you wanted to. We're going to see, actually I'm not going to do it with IP. I'm going to do it just with socket to socket and no IP address at all, no port. No internet address is going to be bound to that. Actually, I shouldn't say that. I believe I am. I'm probably going to use the host name. I'll probably use either the name of the computer, and that's the one thing you'll have to figure out is, well, how do we know the host name? You can send host to host. You can send client to client through ports that are bound on the same client, the same internet address. So messages that are sent to a particular internet address and port number can be received only by the process whose socket is associated with that internet address and port number. And the process may use the same socket for sending and receiving messages. So, and in fact, what you do is essentially you put up a server and you have the server wait and you open up client windows and you send messages to the server from the clients. That's what you're going to be doing. So moving from interprocess to distributed communication, in terms of the way that the distributed system breaks up the previously monolithic applications into different components and then proceeds to place them on different systems or different tiers, as we talked about yesterday, where we are decoupling the consumer and the supplier, client and the server. We are spreading the activities of the application over team players or systems. This is where we get the and this is going to be an analogy. I'll kind of read through this. It's kind of hard for you to read yourself if you're sitting out there. But then we get the analogy of tiering it. So here's the analogy that's going to be here. So let's imagine for a moment we have a small business running on we have a single entrepreneur running a small business. This one person, Suzette, who's the seller, does everything in one application. She sells like customer orders, new products, manages books, pays bills, does everything internally. She is compartmentalized her job functions. So unfortunately, selling and ordering and administrating is all done together in a modular. We would like to make this a more modular kind of component, so there's no overhead associated with the external communication that she's doing. So when her store becomes successful, she finds that she simply cannot do it all, requiring assistance. So long story short, what she's going to do is break out the applications into separate applications, put them on different computers, network them together, and share the data. And voila, we have modern day computing, which is essentially what we're doing. In order to separate it all out, share the data, we have to have port abstractions, and we have to have a network condition in which we can actually send and receive and synchronize the information back and forth. And so here we have, think about two programs on a computer. They can communicate via files, shared memory, pipes, other constructions. So if we're familiar with processing Unix and Linux systems, we have multiple commands that often are strung together with pipes. So the pipe abstraction actually helps you kind of conceptualize how you're passing information between one application and another, because we can pipe it. So, the store itself moves to different offices, to different buildings. Anyway, this scenario is kind of stupid. It just kind of goes through using one computer, separating the programs out into multiple computers, piping the information back and forth, and then now setting it up on a network with middleware so that you can actually string the applications together from distributed systems versus a networked system, like a local LAN area network. So the solution is essentially to make it more dynamic in terms of computer analogy. Now you have a client and a server tier, so you're taking a networking, turning it into a client-server model. We have many different solutions for different files and sharing of information. Generally, we don't think of pipes on a client-server model. We think of pipes on a local application model. So if we take one computer, let's say it's a Unix box, because that's the only way we're going to use pipes. We don't get this in a Windows environment, though. Well, no, we can't get this in Windows. Can't do this in DOS. Where you have multiple applications running, you could set up a pipe link that sends from an accounting program all of the data to a reporting program, and the reporting program prints out the reports of all the data, but the reporting program doesn't have that data that the accounting program has. Instead, it's piped. So in terms of the pipe concept, we have programs all the time that do this through driver interfaces, especially on a Windows environment. Classic example, I don't know if you've ever heard of it, but Crystal Reports, third-party program, very popular, used with Oracle constantly. Well, it's Oracle, it's a client, it's a server database. All it has to do is connect to the database through the internet protocol or through whatever protocol happens to be in place, depending upon how it's configured. It goes in, logs in, and it's a remote application. It's a remote telnet, not telnet, but it's a remote login to it, seamless through the application, reads the data as if it were part of the application, prints it out, does all of its queries. And that actually would be a distributed application development environment where you've got a database on a different server and a Crystal Reports on another server or another client program. Connects through it, you don't know there's a connection, but there is a connection. And the user who's running these reports has no idea what's going on. And then it essentially enables you to use the data, share the data. So moving from an interprocess to a distributed communication environment, I must show this specifically, the location of each one, or the phone numbers being communicated, or the IP addresses. So it's location oriented. Conversations will be slower. We have network latency, obviously. Data will need to be shared between the different ways. So some of the thoughts are, the database and stuff like that. Difficult to draw pictures on the phone. And finally, the phone lines can go down, so you might have issues associated with that as well. So the benefits of spreading everything out, more retail floor space, yeah. But you have to introduce complexity and latency to the business itself. And if you place things on different physical locations, you actually have more fault tolerance, because especially if you have a power outage at one location, you can maybe remote to another location. You can have duplicate locations, duplicate things. And the stage is now to discover how to implement the distributed communications. One of the, and I kind of just didn't do this example very much justice by going through it so quickly, but it's leading to another part of the example I sort of left out was if we take and break things out manually without middleware, is what this is doing. It's just taking and using regular IP, and it's using just regular old protocols to connect all these different applications and pipes and things, right? Slow. That's why people like RMI and they like middleware. Faster. It takes care of the latency issues. It takes care of some of the communication protocols, and it streamlines everything. So although I said RMI kind of runs a little bit slow in terms of if we end with a deadlock or we end up with a busy wait kind of situation, but overall much faster than writing manual port programs, socket programs, much faster than that. And it creates the middleware layer that we're going to be. So Java's choices of the middleware layer, ignoring the platform, because Java is, in theory, ignores the platform. It runs on its own, exactly the same platform no matter which computer you put it on, the Java-compatible runtime environment. RMI is actually a VM, sort of. It's actually its own VM, but it's not a VM. It's a middleware, so it's kind of going to the definition of that. So we're not yet concerned with the capabilities of the application, which we're exhibiting, but to create a server component that holds the desired properties and a client component and requests these capabilities, assuming that the distributed Java database application will communicate via TCP/IP protocol, which it does. So in terms of the, why are we going back through this? Hold on one second, let me just see where we're going with this. Okay. So in terms of the protocol, what we're going to do is I'm going to run through UDP first, actually. And I can kind of skip through this. The lecture seems to be a little redundant in terms, and it's a little low level. So it is lecture 4. You can download it and read it at your own pace. But in essence, for keeping the class interesting, because I'm not going to go through UDP communication one more time again. So I'm going to summarize for you and then hit the examples for you. Because those are really going to be, and maybe I'll summarize it for you, and we'll take a little break maybe, and we'll hit the examples. So the basic, and what I'll do is I'll start with UDP first, actually. So in terms of the protocol stack, it is connectionless, as we've seen so far. It's stateless in terms of fire and forget, or throw the ball and forget. So once the IP packet is sent, the sender simply doesn't care about it anymore. So we're going to build a server that's going to receive stuff, and we're going to build a client that's going to send stuff. And it's going to wait. If it does wait, if it doesn't wait, it can wait or it cannot wait for a server to come back, actually, and tell us something. It's not reliable, as we're going to see. On a downside, it's not reliable. On an upside, it's quick. So think of the IP as the simple postal envelope. So we're going to easily, it can easily be damaged, easily be lost, which makes it unreliable. But very convenient. So the GRAM is implemented on top of the IP layer. It's fairly straightforward, lightweight protocol. Guarantees a single UDP packet that will arrive exactly as it was sent. There's no translation, there's no breaking it up, there's nothing essentially going on with it. And it's stateless, we already got that down. Connectionless. Design considerations. Here we go, this is something different. For the client-server application, the transfer is relatively small amounts of data. So UDP is actually nice for little client-server kind of things. Simple, for simplest type of applications. So in a DNS server, it does not respond after a couple of seconds. A client will simply accept that no answer is going to be forthcoming, and will either ask another DNS server or return an error or something. So here's the example we're going to go through. So we have a UDP communication. Can be implemented with Java quite easily. We're going to use Java for it. So I should point out that UDP is simply a service. It's a service ferry. It's kind of like a sushi boat from point A to point B. And it does not understand the data types or the Java constructs, such as objects. In fact, all it knows is you just send. Well, we'll look at the code in a few minutes. So to accomplish this, and the capabilities, we're going to use capabilities of a string class. So we'll create a string for the message to convert itself into an array of bytes, and we'll send the string as bytes across, back and forth. So simply relying on the string classes, correctly convert the array of bytes using the correct code set. We'll use some automatic methods to convert it. And both the client and the server will perform the same type of operation, but the server has an additional task of it's existing in a state where it can receive requests. So we'll make the server so it sits there in a loop, kind of a state machine, waiting for a client to connect to it. And the client, on the other hand, can execute on demand. It can come away You have many different clients that all connect together. So the way this works, and the first example we're going to look at is called UDP Server Simple. And to get that example, I'm going to go to Firefox here and show you where this example is. It's on the bhacker.com website. It is in Lecture 4, I believe. I'm just going to try to make sure it's still here. Lectures. We've moved on to Lecture 4 source code. When we download it, it's going to be scode.zip. You can see that. Actually, I can't see the bottom of the screen, can I? No. Oh, there it is. scode.zip is the file you're going to download. I've downloaded it, and it should be sitting on my desktop. Let's see. Let's see how I can get to... Well, let's just leave this alone for a second. I'll exit out of here before I go into it. So the UDP server may look complicated, but it's actually, there's very little for it to do. It's going to be kind of simple. The server first creates a socket, and which is a logical abstraction for which is going to attach to a port. So we create the socket first, attach it to a port. We're going to hard code the port in this server to listen to 7777. It's just going to pick a port. In fact, it doesn't matter which port you use. It doesn't matter at all. You may choose any port between 1024 and this is going to be the open ports, essentially, assuming that it's not already in use by another program. If you test this multiple times, switch the ports, because you might have the port blocked by a thread that has died, that is still around, that is still attached to the port in your program. It's going to make your troubleshooting a nightmare. So the server attaches to the port and then performs an endless loop of listening for an incoming message and sending the same message, known as a datagram, back to the sender. So the effect is similar to a mirror. So we're going to see UDP server simple. So someone's going to have to remember that for me. UDP server simple. The client is going to look just like it. It's going to be UDP server client, probably, or an UDP client simple, probably, is how I've got it labeled. It's going to be in that zip file. It's much, this client seems much longer in terms of the source code, but it's added the ability to specify the message that's going to be sent. So it's going to pull it in from the command line, I believe. Has the server name, the port the UDP server is listening to. The approach should allow you to run the program from any client window on the same computer or from different computers. You don't actually have to run this from the same computer. I can send a message to you, actually, through the IP that's running through this wireless network, using the same protocol. But it's easier for me to show it to you just to show it here in both windows. So this client's going to be very similar. It creates a socket, bounds to the network port. However, it's going to bind to a different, it will not bind it to a particular port because we don't care which port it's on. We're not going to return the port. We just know that it's going to send something to the server. And so in terms of it, this is going to be called UDP client simple. So UDP server simple and client simple. It resolves the name of the server, first argument, the IP address, which is the UDP protocol that it's going to require. The second argument is going to be the ports. Let's just take a look at it. Better to just take a look at it. So, what do we have to close that? So here's my S code. And I'm going to, I believe I've got JGrasp on here. I do. So let me just find these guys here. UDP server simple and UDP client simple. These are the two guys here. This is going to be part of your unzipped file. If I double click on it, hopefully it won't bring it up in Xcode. If it does, I don't like Xcode. Okay, I'll show it to you in Xcode. I'll run it from a command prompt so you can see it. In fact, I'll compile it from the command prompt too so you can see it. Because I'm not a huge fan of the Xcode interface. And you still have to exit out to see it anyway. But I do have JGrasp on here. I could show you in that as well. But let's just take a look at this. So the two basic Java, and this is not the EE version. Actually, this is the regular JDK. You don't need the EE version for this. Sockets are supported on the regular one. So I got the Java net. You need to import that one, also the I/O. And here we have the UDP simple server, or server simple as I might say. And we're using a datagram socket. It's because it's UDP. The object is the socket, and it's of the data object type datagram socket. So we're going to do a try here, and this is the port the server will accept the incoming requests on. So we're going to set the server port, and this is just an integer value to 7777. We're going to bind the socket to the port. So this is the socket up here. It's going to be equal to, this is actually just a reference. This is a referenced object, and this is the initialization of the object and creating a new instance of it. So new datagram socket from the server port, using the server port as the parameter. Can't get any easier than this. Declare a storage area to receive the byte. So this is going to be a byte array that's going to come through the stream from the socket. And so we're going to put it in buffer. We're just going to call it buffer. It's going to be new byte array 1000. So we could possibly, if I sent a big message, it could possibly exceed that, but that's a big enough for small little messages. So as a server, we will listen forever until the program is forcibly shut down. So because this concept of the server is just to have it listen. So while true, that's a pretty bad loop. So wait for incoming requests. This is going to be printed out to the screen. Create a datagram packet object that can accept the data from the socket. Pass it to the storage program, the buffer that we've created. Here's a character array. And carefully also pass the total length of the storage area so we know how many bytes were received. So the datagram packet incoming request is going to be an object of the type datagram packet, which is going to be a new datagram packet. It did this all in one shot rather than separating it onto a reference and then an instantiation of the object. So we have a new datagram packet, which is going to have the buffer plus the buffer.length. So we're going to pass it the length as well, so we can take that information in and see exactly what was received. And then we're going to request data from the socket itself. If there is no data, then the request will block. It means it just sits there, i.e. wait forever until data comes in. And so which could cause a problem if we had a bad network connection or something. So here we got the socket receive. So we're running the method receive on the socket object, that instance of the object that's going to look for the incoming request, which is going to be that data that we're going to stick in the buffer. And when it's received, we're going to print out received a message, and we're going to create a new string, and the new string is going to contain the contents of that message. So we're going to get data as a method off of the incoming request. And then we're also going to get the incoming request at getLength, running a method to get the length of the request of the data. And then we're going to create a new datagram packet to send something back out to the client. So hey, we received it. And basically this is what the client's doing. This is the client code actually who's going to be sending the message to the server. So we create a datagram packet object here. It's going to contain the same data received. So it's going to say, yeah, I received this. Here's what I received. Plus the address to go back to the sender. We can actually get the address by doing a getAddress method. So the incoming datagram packet that's being sent from the client to the server is encapsulated with a bunch of data. As an example, we can get the address, the port, everything is enclosed in that UDP packet that was sent. So there's no reason why the server even needs to know about where the client is. It doesn't know until it receives something. Then all of a sudden it goes, hey, I got this packet from this port, from this IP address. And it can get it through methods from the socket abstraction that's created, actually. From the datagram packet abstraction that is bound to the port of the socket. From the socket that's bound to the port. Long story short, it's encapsulated. So we can send the datagram back to the sender. But once we've sent it, unless we have a datagram packet that has come through, we have no idea what client is out there. The client is like dumb. And the client's just out there. So we can send it back, and then we can say reply back. We sent it back, and we're going to print it to the screen. The bottom here is just the error checking, and this is a good idea to do some socket exceptions and some I/O exceptions. And we have a finally down on the bottom. Always remember to clean up after yourself. So finally make it close the sockets essentially. If not, no big deal. It's a good pattern to do that. So let's see if I can find this guy. I'm just going to go out to a terminal prompt here. And, there we go. Oh, it looks big. That's good. Let's just, I need to go to the desktop, I think. Yep. And I need to go to S-code, I think it's called. Let's just see. Yep. S-code. And you may do this actually in DOS. In DOS, whether you're doing it on a Windows machine, is going to work the same as a terminal prompt in my Linux box here. Java C UDP server. Whoops, this requires me to type server simple.java. It'll come back. Yeah, I have faith. And I don't remember how I'm supposed to start it, so let me just do it this way and see what. I can't remember the parameter order, but I will soon find out. It may not actually take any. It does. It's going to take. Well, let's see what it's going to take. Let's just take a look. Let me just take a quick look here. Actually, I got a better idea. Let me refresh my memory on this example. It is in here, actually. Oops. No, it should just run, huh? Okay, hold on one second. I'm sorry? No, it compiled correctly. Oh, okay, that time it worked. I'm not quite sure what I did before. Perhaps it was the path I put in. Yeah, but that's generally, yeah. Okay. I'm thinking. I was working on a different machine earlier today, so I was thinking something else when I wrote that. Anyway, so as we see here on the bottom, we have the UDP server, and we're just going to leave this alone. I'm going to leave this in this terminal prompt, and I'm going to go back and let's take a look at the client code. I'll load the client, and then we'll send some messages back and forth. And I believe the client, let's see. Yeah, it was my on another machine, actually, if I run it from the local directory, I actually have to specify that it's in the local directory. So that // is telling me it's in the current directory. So, but on this computer, not Linux box, it's a MacBook. I keep forgetting. So BSD Linux is a little bit different in terms of its path resolution, and the environment's set differently. So, okay, so what do we got going on here? We have the UDP client. Perfect. So what are we going to do here? This one does take on arguments. We have to basically tell it to go to 777, and we have to send it a message, I believe. So that one I will have to kind of refresh my memory. Well, I think it's just the port here. Actually, I can just do it right now as I'm looking here. It's going to take 2 arguments because there's 3. There's going to be the name, and there's going to be the 777. I think it's 4 sevens, if I remember this correctly, plus the string. So this one's basically going to do the same thing. We have the socket, which is going to be a new datagram socket. And we have the internet address, the host. And with the same 2 includes, obviously, the .NET is actually what's giving us this basic ability, socket abstraction. And so the net address .get by name. So we need to look up the actual IP address of the server name that was passed to the second argument by the command line, which is would be, in this particular case, I believe I'm logged in as bhacker, actually. So I could use, or localhost actually might work, but I can use the local machine name, or I can use the IP address. If I do an ifconfig on, I was going to say ipconfig, then I think it's ipconfig is on a DOS machine. I think it's ifconfig on this one, yeah. And we'll see what happens, actually. This will be a nice experiment. I believe I can use the name of the machine, however, as well. So I'm going to try that first. I get the port of the server that you're listening to. So this is going to be the port number. That's going to be the second argument. So yeah, I guess it is going to be the first argument. I believe if I leave the IP address off, it'll look at the current one. But we'll see. So we're going to pass it to 777, which is going to be the port. So we have the name or the IP address, we have the port, and then we're going to have the message that's going to be sent. And they're going to be bound to, this is going to be the address of the host, this is going to be the message here, that's going to be put into this array, the message, which is going to be a byte stream. This, you have to send it bytes. It doesn't understand formatted strings. It doesn't understand integers and floats and stuff like that. So you use a byte format for that, a byte array called message. So the server port here, and I mean, this is the same as before. This is the datagram packet for the outgoing message. It's going to put the information of the bytes into the datagram packet, stamp it with the address of the host, the 777, and send it off to the server port and the host name, whatever happens to be the IP address that we're going to use there along with the server port, which is the 777. Then the sending of the message is the socket.send. And it's the same thing that we're going to use for the reply back on the server. And it sends the outgoing message to the destination server. And then it's going to print a little message to the screen that says sent the message. And then we are going to declare a little storage area to receive a reply back. So the reply back is going to go into a buffer here. And then we're going to use the datagram packet. And you can obviously download the example and read through all the notes on your own. I'm just trying to save you some mental anguish having to listen to me speak, so by going through it. But the datagram packet, here's the reply message, and the reply message is going to be sent back and say, hey, got your message. Or actually, the server is going to say, hey, got your message. Here it is. You sent me this. So, and the packet.receive is the receive the reply back. It might be, thank you or something, or hey, I got your message, whatever it happened to be. Print out by going get length, get address, get the port information, and print out the stuff on the screen that came back from the server. And so the reply was, this is going to be the stuff that's being printed out. And after what was received, what was the reply? And then this exception handling at the bottom of the screen here. So let's compile and run that one in a different. So let me make this a little easier for you to see. Actually, I'll make this bigger once I set up the new screen. So back at the ranch, we have the server still running. I'm going to open up, oops, I have to open up a new shell. New window, here we go. And let's see, remember this part already. Let's code. What was it? UDP client simple.java. There we go. And now I'm not going to use the dot. I'm just going to go to UDP client simple. Hacker. Let's try that out. Let's just see if this works. Is it 4 sevens?
4 sevens, yes.
I'm logged in on this machine as Hacker. That's why I think that's going to work. But let's see. And this is a test message. Do I need quotes? I'll find out. IO exception received concerning IO Hacker. Okay, which is good. It means my exception handling is working. It means that my port probably is okay. 777. Let me just check real quick here and refresh my memory on the syntax of what this actually needs. I have it in the slide set, believe it or not. Interface simple server. Client, here we go. What is it? Oh, alpha. Oh, I had to put the string here. Okay. All right. I guess I could have just. Let's just check real quick here. Oops. Otherwise, I might actually have to change that Hacker to the IP address of this computer. It may not actually be recognizing the Hacker. Let's just see. No. Hold on one second. What is my? I am. Where's my IP address in here? Say that one more time. Hold on one second. I'm just going to take 1 second here and actually look at this here. 1, 2, 7. Let's try something else here. Let's leave out the Hacker. Quick here. It might actually pull it because it's on the same machine. Nope. Okay, so it's going to have the server, the port, and the message. I am Hacker. Try something else here. If not, I will take a little break. I'll figure out what it is, and I'll come back. I don't think that's going to work. Oh, it did work. Localhost. All right, see? That is troubleshooting on the fly. If I had spent long enough to look at the IP address instead of using localhost, I could have used the IP address of this computer, which is what it was looking for. At home, actually, my network is bhacker, perhaps. I'm not sure. I haven't ever ran it from this Wi-Fi or from this location before. I don't know if that would actually, it shouldn't actually have anything to do. It's computer specific. You're right. So let's see what happened here. So on the client side, we have success. We have sent a message. This is a test. And then we have received a packet of 22 bytes from, here's my address right here. So I could use,
localhost, the 127 is localhost.
yeah, it's localhost, 127.0.0.1 is localhost, you're right. So you could use 127.0.0.1 or localhost. It's easier for me to remember localhost, actually. So the reply back was, this is a test message. And so if I look at the server, it says it was waiting for an incoming request. It received that this is a test message and it sent the reply back. So this is a good troubleshooting example for you, actually, because you may end up with a similar situation. Use localhost, long story short. I believe I have actually used bhacker before, but it may have been on a different computer, actually, and it may have been configured differently. And I want to say the last time I tested this was probably on a Windows machine. And the Windows machine might have a slightly different naming kind of convention to it. Yes. Well, localhost is 127. This is localhost is this address here.
But isn't it the back address that we can use to test the connectivity?
If you're on the same computer, I'm running it to, I don't know if I understand your question, but I'm running the client on the same computer as the server. So, and my client address is localhost, is the 127.0.0.1, which is where the server is located. If I was on a different computer, if this guy here, if the server was on a different computer, I would have to actually specify a different server address. And it could be, in fact, if I had an open port on another computer, on my website actually, if I opened up a port into here, no, actually it is open. I could run it from an internet address. I could run it from an internet address. If I have the server, if I were able to tell it into that internet address, run the server on that address, bind it to a socket that was open to the public, not firewalled, then I could send from a client from my computer, and I would use the server address of that IP address of the location out there. So it doesn't actually have to run from the same computer, but you do have to have an open port, which is the issue. Most servers aren't going to open up the ports like that. If you have a home computer, you have two computers all in the same network, and you have these two telnet boxes can be on separate computers. In fact, I can go and open up another telnet session and also connect. Same way. So if I go, actually, if I, hold on a second. It's going to be the same. And my parallels is going to have the same. I believe bhacker works for my parallels window, though. Maybe during the break I'll try that because I'm sort of curious now. Wait a minute, this is what was this? A simple client? Simple client. What did I do? Did I spell it right? Simple client. Wait, babe. Hold on one second. It's time for a break. I'll say simple client simple. I'm like, something's wrong with that. Client simple. And let's just go localhost again. Localhost. And 7, 1, 2, 3, 4. This, no, let's switch to something else. Hello from ITU. Let's do that. So it knew, it didn't send it back. There's a reason why I'm doing this is to tell you that it knew that this one was a different port. Although it was on localhost, it actually is a different location. This client received the message back, hello from ITU. This guy didn't get it because it's a different client. It actually knows the difference between the different clients. You could easily, and this guy received it, hello from I2. So it's keeping track of the different client connections through the port abstraction because it's all on localhost, but it knows the port is different because this guy is going to be on a different port than this guy. So we can manually put this guy, or we can pick one at random. I believe this is picking one at random, and we're not returning it because we're not interested in it. I'm not interested in knowing where the client is sitting, and it doesn't really bother me. I don't really care. So you can kind of see how the UDP abstraction works, and this is not a bad time to show you the assignment that you'll have to do. And for those of you who are sitting here or listening to the video who are going to be doing the assignment, I practically did it for you a few minutes ago. So we have, last time, in fact, after the break I'll go through the rest of this stuff, but let me just go through this one real quick because it's relevant to what we just talked about. The first assignment for the course is, I believe, a review of Java. And the Java review is writing some simple little programs. You're writing 4 small programs. You're going to zip them together and you're going to upload them as one file. If you can't write these 4 programs, I highly recommend dropping the class. Because this is, if you can't write the 4 programs, you're not going to be able to do anything else. And this is much easier than the object-oriented programming and Java course programs. These programs are writing without using any object orientation. They are just creating one to take the first name and last name from the command line argument. You need to do that because all of the programs that you're writing, especially the one you just saw, is using command line. So you got to be able to do that. Calculating out some simple math, parsing integers and stuff like that. Proroguing, here's another one that's just using a switch case, which is what you're doing actually with networking applications, because you're taking in and saying, did it come from this client? Did it come from that client? Did it come from this client? Because you got to know which client to send it back to if you're managing a whole pool of messages that may have arrived, especially if you're building a chat program. In fact, you can easily create a chat program with this. You know why? Because the server knows about all the clients that are sending him messages. You put them in an array, and you've got all your simultaneously connected clients. One client can send a message to the server can send it out to a different client. Same message. And what have you done? You've just created chat, which is the essence of chat. So you can easily turn this into a chat program if you wanted to. And so the purpose of this first assignment is to make sure you have those skills in terms of being able to take command line arguments. The second assignment is the one that I'd like to show you before the break here. In fact, let me zoom it in this way because it seems to be clearer when I go this way with it. This is assignment number 2. These are not the projects, they're the assignments. The first 3 assignments are programming related. The last 3 or 4, whatever they are all easy. Yeah, they're just like theory questions. So assignment number 2 is the one I pretty much just gave you if you followed along. It's the same thing. You're writing 2 versions of the following program. You're going to do one in UDP and one in TCP. We'll take a break and we'll see TCP in the next lecture. So you need to submit 4 files. A server, a client for both. And what are you doing? You're going to create a password client application which communicates with a server application, and your client will ask you for both a username and a password and a list of legal ones. You're just doing some checking. You're sending a password over to the server, and the server's going to see if it's legal or not. Or the client's going to see if it's legal or not. And it's just nothing more than manipulating a string. The interesting thing is if you have a password string, you'll have to take the string and convert it to bytes, which is the key for this assignment, actually. And the example that I gave you, the simple client, simple server, doesn't convert it to a string. It doesn't work with a string. It only works with bytes. So it takes the bytes from the command. It takes the argument from the command line, puts it in a byte array. So it's actually easy. It's one simple translation that you'll have to do to cast it to a string, essentially. You can use string buffer. You can use anything you want to play with the string. So what you're doing is you can hard code it if you want, a list of legal passwords that can be used on the server name, on the server machine. So the client will pass the information back to the server, which checks it to see if it's correct, and then the server will let the client know whether or not the password was correct or not. It's the same program that you just saw, sending it. Yeah, you can just put 5 passwords in there. The trick is getting the bytes converting it to a string, checking it with the other strings that happen to be there for available passwords, and then sending a message back to the client. I should have put a chat. I used to have a chat one in here, and it confused too many students. You know, create a chat program. This is just doing a password checker as a theme. And you're doing the same application in both the TCP and the UDP. And we'll see there's not too much of a difference between the two. Your server should set up an application, which means that it should work when the work is done. Part of the static main function, it should create a socket at some port. Choose one larger than 1024, hopefully. And await for the client, just like the other example of the server I just showed you a few minutes ago. And then the client makes contact with the server, sets up a stream, sends the information to the server, the name and the password, yada yada. So you can also use exception handling. Not a bad idea, as you've seen in the example I demonstrated for you. Comes in handy sometimes to even let you know what's going on. Just to show you real quickly, number 3 is a answer some questions. Number 4 is answer questions. Number 5 is answer some questions. Number 6. So the first 2 assignments are programming related. So between now and next, because you already have the information for both of the 2. So between now and the second weekend meeting, do those 2. In terms of the programming projects, those you're going to want to wait for number 2, 3, and 4. Number 1 you can do. Number 1, and we just demonstrated yesterday, it's the JDBC program. Number 2, I believe, is RMI. It is RMI. Number 3 is servlets. So number 2 and number 3 you're going to want to do after the next weekend session. Number 4 you could probably do. That one we looked at yesterday. That is any protocol you want. You can use UDP, TCP. Let's view this here. I don't know why these are smaller. It's kind of weird. And maybe it was the computer that I created it on. Number 4, this one in particular, you can probably do if you wanted to, because you could use socket abstractions for it. You can use your UDP or your TCP. You're probably going to want to do this in TCP, actually. But this one is creating a any program using any protocol you want. Actually, if you wanted to, let me just read this real quick here. Since I should count down. It's giving you the description here. So you're creating a client-server program. The server has a very simple job. It launches a rocket ship to outer space, and the client connects to the server at a certain port. We just saw that with a UDP. And the server waits for the message by the client. The client sends a message back, launch, and it does a little countdown. If you want, I'll tell you right now, if you want to do the chat program, because I think that might be fun, actually, you can do that instead of this one. So I'm just looking for any program using any program of your choice. For those people who missed the video or missed the lecture, they'll probably end up doing this one. But if you want to do a chat program, I'll accept that one as well. But we've already seen how you can do the chat real easily, actually. And it might be fun to actually set up like 5 clients and have them chat to each other. And you use the server essentially as the message exchange. And it knows the port of every one of those clients. So it can go back and you can send the message to whoever. You will actually have to add a second parameter there, though, because it knows where the message came from, but it doesn't know where the message is supposed to go to. So you pass in another argument that says destination ports, and you give it the port number. But in order to do that, you got to know the port numbers of all the different clients. So there's a trick to that. It's not quite as straightforward as you'd think. It is half written for you already, but you have to keep track. Everybody has to know everybody else's port number. And you can, not fix that in. How does Yahoo do that? Well, easy. Names. Your name's attached to a port number where you're sitting. Every time you log in, your name is registered on a list, and you get, goes in bold, or it becomes active or whatever. It means it's attached to a port. So if you sent a message, the server's going to know which port to send that message to. So. Okay, let's see. It's a 12:03. How about we take lunch? How does that sound? Are we ready for lunch, or we want to? I'm ready for a little break, though. How about we take a lunch break until, how long do you guys want? Till 1? Okay, we'll come back at 1 o'clock. Take an hour. That's good. And that way I can play around with my TCP. Actually, I'm actually going to play around with my Windows and see if I can use bhacker on that. But all right, so I will see. Yes.
Where are the videos located?
Oh, let me end this video and I'll show you real quick. Any questions, comments, or concerns before we break? No. Okay, good. And we will come back at 1 o'clock. So this is the end of part 1.